All right, ladies and gentlemen, welcome once again to the Simpkins Physics Corner. I'm here with my guest star. My son is in the background, so if you hear some interesting noises, that would be him. But I wanted to walk you guys through the basics of energy here this morning. So welcome back. It's a Monday in the calendar this year, but you can watch this video wherever you are and whenever you are. So here we go. Let's jump into it. Kinetic energy, we talked about that as the energy of motion. So that's going to depend on the object's mass and the object's velocity. And from that, we get the equation, kinetic energy equals 1/2 mv squared. So when I write KE, that's like all one big thing. It's kinetic energy equals 1/2 mv squared. Now, kinetic energy is what's called a scalar quantity. And if you remember earlier this year, we talked about scalars versus vectors. A vector has magnitude and direction. Oh, yeah, but a scalar just has magnitude. So it means what? It means it doesn't have direction. I'll just put no direction. All right, and all that basically means is that you shouldn't get a negative answer, and that actually makes a lot of sense when you think about it, because even if the velocity is negative, what happens when you square a negative? Oh, you get a positive. So that's why kinetic energy has no direction associated with it. So, of course, these variables, they mean the mass is, the m is going to mean mass, and that's going to be measured in kilograms. So you want to be heads up for kg, the kilograms in a problem. The v, of course, is going to mean velocity or how fast you're going. So sometimes maybe it'll show up as speed, but of course, velocity would be in meters per second. The mass would be in kilograms, and then the KE means kinetic energy. Sorry, I pinched myself for space, but just a reminder that energy is measured in joules. So two quick examples calculate the kinetic energy. So we want the kinetic energy of a 8,000 kilogram airliner flying at 216 meters per second. So don't forsake all of the good techniques that we've learned and used this whole year. You always want to write down this list of knowns, and as I do that, I realize I need one more zero in there. We're flying at 216 meters per second. So we've used enough meters per second all year that you know that the velocity has to be in those units. So now it says calculate the kinetic energy. You can see how easy this is if you write the knowns. If you don't write the knowns, it's probably going to be a little more tricky to figure out. But if you do write the knowns, you just go ahead and plug those in there. 1/2 mass is 8,000. I'll write it correctly this time. Kilograms, and 216 meters per second. And we're going to square that whole thing. So just be careful. Some people, the way they, especially if you use your phone as a calculator, which don't get me started on that. And the reason I don't get me started on that is because the phone's calculator usually has horrible syntax rules, which means you type something in and you think it's doing something, but it's interpreting it as something else. Oh, it's to say 1/2 times 8,000 times 216 squared. We're only squaring that last number. Now, it's still really huge, okay? So let me start writing this. This is a really huge number here. But again, it's an airliner flying through the air at a really high speed. So 1,866. Good thing there's not another 6. I'd have to throw some holy water up in here. And we got like that. Okay, so that is a lot of joules. That's 186 million something joules. But that's how much kinetic energy an airline would have flying that fast. All right, if we continue down here, we got kilograms and joules, and it says how fast is it moving. So this, let's go ahead and write our list of knowns here. We have a mass of 0.24 kilograms, and we have a kinetic energy of 23.52 joules. How fast is it going? That's asking us to solve for the velocity, how fast. All right. I just packed away a bunch of toys in a box. My son is currently throwing them all over the room. So, yeah, and he found an airplane too. So how fast is it moving? So we have kinetic energy equals 1/2 mv squared, and we're going to go ahead and plug kinetic energy over here as 23.52 joules equals 1/2 0.24 kilograms times v squared. Did you find an airplane? You know, he's so excited because we just did a problem about an airplane, so he's following right along with us, even though he's 21 months old. So are you following? You should be, because if he can hang, you can hang. So we're going to go ahead and do this, and I'm going to change colors here because we got 23.52 joules equals half of 0.24 would be 0.12, and that would be times v squared. So to solve for velocity here, there's a couple of algebra steps involved, but if you take your time, you can get those algebra steps. So the first thing you want to do is get the v squared by itself. That means you have to divide both sides by 0.12. All right, and if you do that, you get 196.27 equals v squared, and then of course the final algebra step there would be to square root both sides. So take the square root of both sides. We get a nice even 14. All right, so there's two examples of how you might see the kinetic energy equation show up in a problem. It might just give you the mass and velocity directly and ask you to find the kinetic energy, or it might make you use the equation to find the velocity, kind of working backwards there, if you will. All right. The next type of energy is the potential energy, and that is a type of energy that is stored. So it's the potential to do work, as we said in previous lessons. It describes an object that has the potential to do work, or so to fall. All right. If it's raised up to some height, it could fall, and if it falls on your toe, it will do work on your toe. So it could fall or it could do work. Now, two common examples of potential energy. This is the one we're going to focus on the most. GPE equals mgh, or mgy, as some people put it. And then the other one is EPE. That's like elastic potential energy, and we're not going to use that one as often, but that's associated with the energy stored in a spring. So for today, we're just going to look at the GPE, the gravitational potential energy, because we're going to be analyzing the motion of roller coasters with the law of conservation of energy and these two energy equations. So let's use this equation real quick. We got kilograms, meters, and it says how much GPE does he have. All right, so if we make our list of knowns, we see m equals 65 kilograms, and we'll say y is how high, or you can use h for height, that's fine too. But either way, it's got to use the same equation. You'll notice it says how much GPE do you have. Now, you may say to yourself, well, Mr. Simpkins, there's three knowns on the right side of, or sorry, there's three variables on the right side of that GPE equation. Well, we know that g, and since we're on the surface of the Earth here, is going to be 9.8 meters per second squared, just like it's been all year. So then this is just a quick plug in here. We do mgy, and when we plug, I always like to write the equation first, because then you make sure you're plugging the numbers in the right spots. But then we have m times g times y, and let's go ahead and take a look at what that is in our calculator. That's not a phone, so actually we'll get the right answer for me here. Except this one is from when I was a sophomore in high school, so sometimes it needs a little help getting started back up. Here we go, 6,370 joules would be the potential energy of that diver at the top. Okay, and then here, this is kind of like the second example with kinetic energy, where they actually give you the energy and it gives you the mass, and so you kind of have to just dig back and solve kind of in the reverse direction here. But let's take a careful look at what we have. We have GPE equals 5.2 joules, and we have the mass equals 0.4 kilograms. All right. Oh, this guy is hilarious. How high above the ground is the textbook? So we're looking for how high. Y is how high. So that's the one we're solving for. We're solving for this Y in the GPE equals mgy equation. All right, so we're going to go ahead and set this up. We always want to write the equation in terms of variables only first so that we don't misplace anything. And now that we have that, we can kind of just write it right underneath of what all our values are that we know. So we know the 0.4 kilograms. We know the 9.8. And we know the Y. Oh, my son just heard an airplane fly over. Yeah, you got an airplane? Oh, there's one outside. Yeah, is there? You know how much kinetic energy it has, bud? I guess we could find out, couldn't we? 1/2 mv squared. So for this one, you would have to multiply these two things together. Let me use the highlighter here. You have to multiply these two things together. And if you do that, you would get 5.2. Oh, do you have it? Oh, thank you. He brought me a helicopter. Look at that. There it is. That's beautiful. 5.2 equals 0.4 times 9.8, which would get me, try again, 3.92. And that is what I get when I combine those two terms in green together, 3.92. And then the Y is going to be the one we're looking for. So in this case, you just divide both sides by 3.92 to get the Y by itself. So 3.92, 3.92. Sorry, that got a little sloppy there. But 5.2 divided by 3.92 be 1.32, and the answer is going to be meters because it's height. Y is how high, it's height. The answer is going to be in meters. So there's two examples for potential energy. Now, why did I give you these two specific examples? Because our activity that I want you to look at today is graphing roller coaster energies. So let me zoom out a little bit so you can see more of the document at once. All right, we're going to actually track the motion of this roller coaster as it goes through its little journey here. And so down at the bottom, of course, you're not going to have any energy because you don't have a height and you don't have a speed. And so in order to get from point A to point B, you're changing energy. What changes energy? Oh, when work is done, energy changes. W equals delta E, or the change in energy. All right, so this says you 50 kilograms, your friend 50 kilograms, and a cart are all added together. What is the total mass? So of course that'd just be 300 because you're both sitting in the cart, so we'd add you all up together, 50 plus 200. It says at position A, the roller coaster is at the reference level. What is the total mechanical energy at this point? Explain your reasoning. All right, well, at point A, the total mechanical energy, just to reinforce here, is basically the total energy. So it's how much kinetic plus GPE do you have? All right. Well, let's take a look here real quick. Are we moving? Well, it says it's not moving. So we have 0 kinetic energy. Do we have any height off the ground? No. So we have no potential energy. So what's the total mechanical energy? 0. So in the words that I just used, it's going to get too sloppy if I try to write this with my stylus. So I'd recommend at this point you guys could click your mouse there and type your answer. But you can just say something like, hey, there's no potential energy because we have no height, and there's no kinetic energy because we have no velocity. So that would be your explanation. Now, for this one, it says work is done by the chain to raise the coaster up to a height of 40 meters. And then it says how much work is done. Well, you may be at a loss here because you say, well, I don't know what the force is. What would I do with that? But remember that when work is done, energy changes. What kind of energy do you gain if you gain height? You gain GPE. And so all you have to do for this one is type in MGH. Well, the M we said was 300 because that's you plus your friend plus the cart. 9.8 would be our gravitational acceleration, and the height would be 40 meters. So that's going to get your starting number. All right, and so that it would be 300 times 9.8 times 40 for a grand total of 117,600. Now, here's the big idea. I only have a few minutes left for this video. The total energy at the top of the roller coaster right there is 117,600. Okay, what does that mean the total has to be at point C? 117,600. What does that mean the total energy has to be at point D? 117,600. What does the total energy have to be at point E? If you guessed 117,600, you're right. That's because the total energy has to stay the same. Now, of course, the type of energy is going to change. Here it's going to be GPE, and then we're going to gain kinetic energy as we gain speed falling down the hill, and then we're going to be losing potential as that happens. All right, and so it says at position B, the total mechanical energy is 117,600. Which is all in the form of GPE, or gravitational potential energy, because we're not moving and we're at the top. Let's see if I can show you one quick sample of what I want you guys to do in the next few minutes of this video. In this table, you'll see I give you certain pieces of information. So if I give you height, I want you to solve for the GPE. Well, we actually just did that, so that's going to be 117,600. Oh, fantastic. It's just completely moving my annotations as I do them live. There we go. That's how much energy we would have. Now, at the top, the velocity is 0, and so the total energy would be 117,600. Well, because of the law of conservation of energy, guys, this number has to stay the same the whole time. So that total energy has to stay the same. So let me walk you through some steps that you might do. If you have velocity, what kind of energy can you calculate? Okay, by the way, it's not 0. If I did that, it's not 0. Okay, the velocity is 14. But if you know the velocity, what kind of energy can you get? Oh, you can get kinetic energy. How? By using that equation. Okay, now what else do we know? We know that the total always has to stay the same. So the total 117,600. And if you look at the notes that we did today and the activity from the skate park we did the other day, you will see that all you have to do is subtract the kinetic energy that you know from the total energy to get the potential energy. So let me do a quick calculation for you guys here. We're going to do 1/2 times 300 because it's the mass. All right, so 1/2 times 300 times 14 squared. So in this, if I do the kinetic energy equation correctly, I get 29,400 joules. Well, how would I figure out how much potential energy there has to be? Over here, how would I figure out these two things? Well, what I have to do is take the total energy minus the kinetic energy, and whatever is left over has to be in the form of potential. All right, so 117,600 minus 29,400 is 88,200. All right, so it would be 88,200. And just like the example that we did, you can use the potential energy number to work your way back to height. So if you go to the example number 2 for GPE. I'll post a video tomorrow, but what I want you to do for today is to finish these notes and to finish this data table, to do these calculations. Tomorrow, I'm going to show you how to put those pieces of information on this data table over here so that we can take a look at how the potential and kinetic energy exchange through a roller coaster ride. Until next time, this is Mr. Simpkins in the Simpkins Physics Corner.